Hello! In this video we're going to be looking at the theory behind eigenvalues and eigenvectors. So we'll start out with a definition, and that will be about the eigenvalue and eigenvectors of a matrix A or a transformation T. Essentially, our definition says that an eigenvalue, sometimes I call these lowercase ev's, associated with a matrix A or linear transformation T of x, where that T of x is equal to A times x, is a scalar lambda such that A times that vector v is equal to lambda times that vector v for some non-zero vector v called an eigenvector for that matrix or transformation. So essentially, when we're looking at eigenvalues and eigenvectors of a matrix, if I can take that matrix A times a vector v and I get a scalar multiple of that vector, so essentially that matrix multiplication gives me a scalar multiple, or that transformation of the vector gives me a scalar multiple, then I call those an eigenvalue and eigenvector. Now notice that eigenvectors can't be zero because that's sort of a trivial case. A times 0 would always equal lambda times 0, so we can't have that. Okay, so how do we find these? Well, to find an eigenvalue of A, essentially we're going to be using this equation and sort of manipulating it just a little bit. So I start out with this equation, AV is equal to lambda v, and I'm going to subtract lambda v from both sides. So I have a matrix vector minus a scalar vector, that's the vector 0 over here. What I want to do is I want to factor out the v. You know I probably have to do that on the right hand side. But the problem is I have a matrix minus a scalar there, and that can't work. So I'm going to change this into a matrix without ruining the essence of that scalar. So I'm going to put in this identity matrix I here. So I have A minus lambda I of the same dimension of A, so that's I sub n, times v is equal to 0, and this should still be the 0 vector over here. So how do I find an eigenvalue of A? Well, eigenvalues are scalars. So what I want to do, since v has to be non-zero, I need for this to be singular. I need to find all non-zero solutions of this. If it was just 0, then this would be non-singular, this would be invertible, but we know this is going to be singular or non-invertible for this to work. So what I want to do is I want to find where the determinant of A minus lambda I sub n is equal to scalar 0. So this is my equation that I really want to solve to get those eigenvalues of A. So it's going to turn out to be a polynomial. In fact, we should get n zeros from this polynomial. Now they could be repeated, they could be complex, they could be real. So we're going to have a polynomial here, and hopefully we'll get n zeros from that. Those will be our eigenvalues. One thing to notice about our eigenvalues is they're going to be unique. And what that means is essentially that when you find them, they can't be, different. They have to be those eigenvalues that you find from that polynomial, from solving that polynomial, and they can't be any multiples or anything else like we'll see with eigenvectors. And speaking of eigenvectors, well, how do you find those? Well, to find the corresponding eigenvectors of the matrix A above, we're going to go ahead and use that same equation, AV is equal to lambda v. We're going to manipulate that to our equation star. So essentially what we're going to do is solve this equation for non-zero vectors v. What that means is that we have a matrix, so this is a matrix times a vector is equal to 0. We know that 0 works, but 0 can't be an eigenvector of this matrix. It's trivial. What we're going to do is we're going to find the rest of the null space. So the rest of the null space of this will be our eigenvectors. So that's going to be finding the non-zero null space of A minus lambda I sub n, where A is that n by n matrix above. So we're going to be using this equation to find our eigenvectors. This will give us the eigenvectors of A, and eigenvectors, as we will see, are not unique. What that means is if I find an eigenvalue, lambda, then the corresponding eigenvector, v, can be all multiples of v as well. So we could find an eigenvalue, all of us could find an eigenvalue lambda, but we could all have different correct eigenvectors v for that eigenvalue. We'll look at an example of this in our next video, but I wanted to start you off with the theory here. Hey, I hope this has helped. Thank you.